Hello people from J4K! My name is Rafael Benevides and I'm very pleased to be here with you talking about Saga Patterns. If you have ever produced a cloud native application where you have distributed databases and you had an issue with transactions, this session is for you because we're gonna see how to solve that problem. Okay, so let's start. If you want to have access to the slides, you can go to this link here, bit.ly/Saga Kafka, because we will use Kafka in this demo. Okay, so you will see a really nice demo on how to have different services with produced using different languages with different databases, including a NoSQL database, and we will use Kafka as an event store for this demo. Okay, so the first thing that you're gonna have that you need to have in your mind is that in a monolithic architecture, usually we have only a single database, and this is not an anti-pattern, okay? Most people think that having a monolithic architecture nowadays is wrong, but it's not, okay? But when you decide to move to microservices, you will have a little bit different architecture. Instead of a single database, you will have one database per service, okay? And that's kind of mandatory, because otherwise you will not have the agility that you need for to justify having a cloud native application. Okay, but if each service has its own database, you will likely have one transaction per database. So suppose that you have here an order service, a booking service, and a payment service. When you open a new order, this will involve a REST call to a single order, and that will create that order in a database. Then the order will call the reservation for a specific room. So that will also call. It will store the booking information in another database, and finally you will need to pay for that booking and for that order. That will go to another database. Each one is a different transaction. And there's no ACID transaction that span all the service. Each transaction is ACID. So let's recap what's ACID. A for atomicity, C for consistency, I for isolation, and D for durability. And we cannot guarantee an ACID transaction that span all services. Okay, so for example, let's suppose an exception: no room available in a synchronous call. So we open one-to-one services involved. We open a new order, then we want to reserve a booking, reserve a room, and in the case of a room is not available, we will receive an exception, and then we just cancel the order, right? That's easy. But suppose that you have payment denied. We will walk one little more service. So we try to make a reservation, that was fine, and then we want to make a payment, and the payment is declined. So in that case, an exception happens, and what should we do? Should we cancel the order? Okay, that's fine, but who will cancel the booking? Is the payment service that will cancel the booking, or is it the order service that will cancel the booking? So we should watch out for Death Star architectures. Okay, imagine that you have 10 microservices to roll back. Can you spot the complexity? So this diagram here gives you an idea what is a Death Star architecture. Okay. And most people can think, okay, that's easy. Let's use a two-phase commit. It's called two-phase commit because we have a phase number one, which is the prepare phase, which the service will reply they are prepared to commit or to abort, and then we have the second phase, which is the commit phase, where the service or where all the transactions will commit or abort the transaction, replying that they are done, committing or aborting. What's the problem? The problem is that this transaction coordinator is the single point of failure in this architecture. And plus, all the other services have to wait the slowest resource to finish its confirmation. So for example, suppose that we have a credit card that takes 30 seconds to reply. During that time, all the services and all the databases are locked during that time, which can cause deadlocks. And in this scenario, of course, the throughput is reduced due to locks. And think about NoSQL database; it's not supported by many of them. Okay, so what is the solution? The solution is to use a Saga Pattern. Saga Pattern is a solution that came from 1987. It's not something new. It was proposed by Hector Garcia Molina and Kenneth Salem. And it uses a state machine. So how does the Saga work? First, the order is created in a state of pending. Then when the last service is called and the payment is approved, then the service is finally moved to approved. Okay, so what about the rollback? For each transaction, we need a compensating transaction. So to create an order, we have the cancel order. To reserve a room, we have the cancel reservation. So imagine the situation. I created the order and called the reserve room. Transaction 1 was called, and when we try to call the transaction 2, it replies no rooms available. So the transaction never completed. That's why we don't need to call the compensation transaction C2 cancel reservation, because that was never completed. We don't need to undo the reservation, and we call cancel order, the previous one, to undo the creation of the order. Okay, and payment withdrawal was never called, and C2 were never called, because, as I said, C2 does not need to compensate anything, and the payment was never really called. Okay. In a situation where the payment is denied, so we're using the state machine, we open the order in a state of pending. Then we have the service, the payment service saying that's denied. So in that case, the order is changed not to confirmed, but to canceled. And once that the order is canceled, there's nothing else that we can do. We cannot open a new payment. It's canceled. Okay, the state machine dies there. But in a synchronous scenario, we have a problem here. So we have the order pending, and we ask for the payment service to proceed with the payment. And what happens if the payment is offline? In a synchronous call, that will be pending forever, because the payment was never able to complete or to decline. So that's a problem. That's why we need to go asynchronous. And that's what we will see now in event sourcing. Note here that this is a brief explanation, okay? So what is event sourcing? Event sourcing is an architectural style where you don't save the current state of the object, but you save the events that led the current state. And that's why order is important. So if events happened in the past. So an example, I have a state here, a blank bank account. So I create a new event. Open account with the ID 123 for the owner Rafael, that changed the state of my object to a bank account with the ID 123 balance 0 owner Rafael. Then we have another event. We make a money deposit in this account of the value of $100. Then we changed that event changed the state of my bank account to have the balance of $100. Now we create an event to withdraw $60 that updated the balance. And if we try to do another event of withdrawing $60, that event is not possible to be handled. So what will happen? The state will not be changed. Okay, we will continue with the balance of $40. Okay. Now we need to understand not only event sourcing, but we need to understand command sourcing. Command sourcing changes a little bit the style, because instead of persisting events, and events are things that happened in the past, we will persist commands. Commands are intentions that we want to perform. And once that we try to perform a command, it waits for replies. Okay, so for example, execute an account withdrawal of $100 plus and 50 cents. That can cause a reply of insufficient balance reply. Okay, and why understanding event sourcing and command sourcing is important? Because when we are talking about Saga patterns, we have two types of Saga. We have a choreography-based Saga, where the services collaborated by exchanging domain events. And when we have an orchestration-based Saga, we have a coordinator that sends commands. Send commands and messages to the participants, which will respond with reply messages. Okay, so let's go deeper now. In the choreography-based Saga, choreography-based, it's just like a dance. They are a dance that was rehearsed pre-choreographed, if you know what I mean. In this case, we have the three services: the order service, booking service, and payment service. And once that we create an order, the order is created, and then we publish an event to the event store saying order created event. Now, why that event is important? Because once that booking knows that the order has been created, it creates a booking and publish the result, booking created event. The payment reads the book created event and publish payments and proceed with the payment, right? And publish payment success. The booking will consume the payment success and confirm the booking, and the order will read that the booking is confirmed and everything, and the use case is completed. Now, in the case of no rooms available, we publish the order and we try to book the room. There is no room available, so the booking service published no room event. In that case, the order service needs to call its compensating transaction. It will consume no room event. Payment was never called. Payment denied. We proceed with the events, and then the payment replies, payment denied. Then it's time now to call the compensating transactions. So booking service knows that the payment was denied, so it cancels the booking and publish that the book has been canceled. The order consumes that event and cancels the order as well. So what are the advantages and disadvantages of choreography? Well, first, the choreography is really simple to implement. Right? You saw it's really simple, but we have a tight coupling because the services are highly dependent of each other. The decision logic is distributed, which is hard to maintain, it's hard to debug, and it's really hard to manage the state. Plus, we need now to understand about event to command transformation. Because if you have paid attention, the order service listens for book confirmed event, so it can confirm the order, no room event to call the compensation transaction, or book canceled event to call the compensation transaction, and so on. So booking has to know a lot of events that triggers an order action. What we should do? Proceed with event common transformation pattern. So an event is something that happened in the past. So in that case, the order is where we do the coupling. So we need to transform that to a command is something that will happen in the future. So we transform that in a book command, perform a booking. Okay. So in that case, we publish a command, booking a command. Will publish the command to perform a payment. Payment will consume that command. We publish a book command, and so on. Okay. Now orchestration based. Orchestration based, we have a new entity there. We have the orchestrator. The orchestrator will the order will receive the method, create an order. We will publish the event. The orchestrator will look for that event and will start producing commands instead of events. So it will produce a command, perform a reservation. So the booking will perform a reservation and publish the result. The orchestration will read the result and say, okay, now it's time to pay for this booking. Produce a payment command. The command will be consumed, and the payment result is published. And the orchestrator, no, okay, the payment is okay. Now it's time to confirm the booking and confirm the order. So now you can see that booking service consumed booking command. Payment service consumed payment commands. And so that's why this pattern reduces the coupling. Okay? Imagine the following situation. Payment denied. We publish the commands. Now it's time to publish the payment. Payment replies, the payment is denied. And now it's time for the orchestration to say, okay, since the payment is denied, let's cancel the booking, let's cancel the order. In this case, the orchestrator sent the commands in parallel. Okay, so what are the advantages and disadvantages of orchestration? Well, first, we have a centralized business logic, everything inside the orchestrator. So it's easy to understand, it's easy to maintain. We have a loose coupling of as each service consumes only their commands, and the orchestrator is the single point of failure. And needs, of course, to reduce the coupling, the event to command transformation. Perfect? But no matter if you are using choreographed or orchestrated, you can have, for example, the order service using being the aggregator for the use case. In this case, the events are sent in parallel. Or we can use it as a chained invocation, where the order service sends the commands to booking that sends to payment. The problem is the aggregator holds the logic for the use case. So when calling the compensating transactions, the aggregator needs to understand what are the states and to undo the logic. In a chained scenario, you just undo the previous transactions. In the orchestrator, we have the same thing. The design is looking very similar. In an orchestrated, having the orchestrator as an aggregator, we can send the requests in parallel, or we can send the requests in serial. Okay, and when we are undoing the transactions, it's of course when you are having the orchestrating calling in parallel, you would need to coordinate the states. And even using orchestrator as a chained pattern, we can just undo the last one. So it's really simple to implement things using the serial pattern, the chained pattern. Okay. Now let's talk about event sourcing with Kafka. Kafka is a distributed stream platform that allows you to have producers of messages, consumers of messages, integration with databases, and also a stream processor. The stream processor is a really nice feature because we can easily create orchestrators with Kafka streams. Why? Because the Kafka streams is an API that consumes, process, and publish messages to Kafka topics. So if you produce a command, the API can read that topic of a command, process what's needed, and publish the result. That's really, really perfect. And that's what I use it in this demo. So let's see a demo here. Okay, I have here some services, the booking, the payment, the order. We have MySQL, MongoDB, just to show that we can use different databases, and of course Kafka running. I'm bringing them with all of them using Docker Compose. Okay, let's wait for them to start. And while it starts, let me also present to you the APIs. I have an API here using Insomnia. Insomnia is configured to use order. So we have some orders operations, including get orders. Nothing to reply. Booking. We can see that we have some bookings here. So we have the room 100, 200, 300, 400, and 500. And the price of them is $1,000 each. And they are free at this moment. And we have the payment. If I get the payment, it will reply for me. Let's wait. With $5,000 to spend. So let's see some use cases here. First, I will try to book a room. So let's book a room here. Let's post a new order. It's just call the method post, send it, and it replied order number 201 created. If I go here to get orders, it's there. Oh, it's pending. Why it's pending? Let's see. There was a pending shutdown. Let me just restart it here. Okay, now he started the servers. Let's see what's happening here. So let me post a new order, order 2, get orders, pending. Okay, now everything is running. Let me show you again. Let me post a new order, order number 3, get orders, confirmed. So you can see that it's very, very, very fast. Okay, now let's do the following. You can see that once that I call, by the way, let's see the status of the rooms. We have room number 100, 200, and 300 confirmed. Room 100 for order 1, 200 for order 2, $1,000 each. So if we get the balance, we have $2,000 left. But let's do another thing. Let's do another use case. Let's take the payment offline and see what happens. Okay, so let's do it here. Docker compose stop payment. Let me do this. Okay, payment is not running. Now let's post a new order, order number 4. If we get the orders, now the order is pending. And it's pending why? Because if you go to the rooms, we have a room that's reserved to the order number 4. But of course, we cannot confirm because it was not paid. And if we try to get the balance, of course, we cannot connect to the server. But let's do the following. Let's restart. Let's start payment. Okay. Docker compose up. So let's bring the payment up. And then if we get the orders, note here that once that service is up, the order became confirmed, because that information regarding the order has been processed by the message was there inside Kafka. So Kafka sent the message to the payment service to confirm the order. The order replied, okay, I will confirm, and everything the use case has been completed, including confirm the rooms and confirm the order. Okay. Now let's do another exception. We have $1,000 to confirm here, to buy things, to buy new rooms, and we have just one room left for $2,000. So if I place a new order number 4, what we will have, order number 5 canceled. An account has a balance of $1,000, but it tried to withdraw $2,000 because that's the only room left. And of course, the balance is still there, $1,000. We couldn't complete the transaction for payment, so we roll back. Of course we didn't complete the transaction for the room, and of course we needed to cancel the order. Now let's do the following. Let's make a deposit of $1,000 for this account, for the account number 1. So now we can spend $2,000. Okay. Let's place a new order. Order number 6. If we get the orders, the order was confirmed. Okay. Now if I post a new order, let's see what happens. New order 7, and the reply is order canceled. Why? Because there are no rooms available. So this there are no rooms available. It didn't even check if we have a balance, because we depend of the cost of the room to withdraw money. So in this case, just the balance, just the booking service has been called. Now let's do the following. Let's release a room. I will release the room 100. So let's cancel the reservation. So now it's free, okay? But what I will do is to stop Kafka, okay? So let me stop Kafka here. Nope, I made a mistake. No, I don't want to stop all the services. Okay, but there's no problem. Let's keep them stopped, and I will start again, but Kafka. Docker compose up. Okay, let's wait it for the service to start, and let's stop Docker compose stop Kafka. Instead of stopping Kafka, I will stop the orchestrator. Okay, so let me start Kafka. And stop the orchestrator, because that's the single point of failure. Stop orchestrator. Okay, now that the orchestrator is stopped, let's try to place a new order number 8. So what it says, 8 is pending. The room is still bringing up. Start booking. And let's get the balance. The balance is also offline. So let's see. So the room 1,000 is 100 is free. Let's get the balance. Balance is not existent anymore. It's zero. So let's do a deposit of $1,000. Okay. So the order is still pending. The room is free and we have a balance. Now, once that we start the orchestrator, we'll see that the use case will automatically complete. So we can see here, orchestrator is up. Now we can see some information. Okay, let's get the order. And the order 8 is still pending. Let's check the logs. For any reason, probably I lost the message when I restarted the containers. But the use case should be completed. Okay. Well, since our time is over, what I want to show you is that if you want to try this demo yourself, you can go to this repository where you will see the source code for booking, which was implemented using Spring Boot, order using Node.js, and payment using microprofile Helidon, and of course the orchestrator using Kafka streams. By the way, you have MySQL and Mongo Express. You can even open Mongo Express here and see the information related to the documents, since it's a NoSQL database. Okay, I hope that you enjoyed. You can reach me via Twitter. My Twitter handle is @RafaBene. Okay, and I will also post the information of my Twitter here. So thank you so much, and you can drop the questions for this session, and I will try to reply easily via Twitter. Thank you so much.